Okay. So in a lot of cases, we think of a graph as a network, as a roadmap, as an idea of ways of connecting things. So the idea of looking at what parts of a graph are close, are related in a sense. We want to think about this and define some terms for this. So let's suppose I have some graph, vertices and edges, and I'm going to say that if I have an edge and it connects the vertices U and V, then I'm going to say U and V are adjacent to one another. But in the same vein, we might as well call them neighbors. I'm in the room next door. See, you just go through this edge and I'm right here. We could also describe that U and V are joined by the edge. Now, sometimes we want to name an edge rather than just look at the two vertices. So I might say, well, this is the edge E. And it happens to connect vertex U to vertex E. So vertices are adjacent through the edge between them. An edge is not adjacent to a vertex. It is actually it, right? It is touching. So we say that it is incident. So if I have an edge and it's got the vertices U and V connected by that edge, then that is the vertices that are incident to that edge. If I want to think about things that are adjacent, I have to think about something being between them. So the edge is between the two vertices, but there's no reason not to have two edges touch the same vertex, right? So I could have adjacent edges. So items are adjacent when they connect through something. Items are incident when they connect directly. Make sense? New weird ass terms. Pictures make this a lot easier. So rather than just list a graph, please note, I did something sneaky here. when I wrote down the edges. And I did this same sneaky thing on Monday. I've written these edges in alphabetical order. U is before V, V is before W, W is before X, and X is before Y. So the first letters are in alphabetical order, and within the second letters, they're in alphabetical order, right? The X, the Y, W, the X, Y, W, X, and Y are in order. This sort of alphabetical ordering is helpful because it means I don't accidentally double write a vertex. Sorry, an edge. That's a graph. But that's useless. Draw me a picture. What does this graph look like? Now, here is where some variability comes into play. You have to decide how you're laying out those vertices. And you can lay them out in lots of different ways and end up with different pictures as a result. I only have 5 vertices. So you can put those 5 dots just about any way you want. Adam, tell me how you laid out the vertices. In a circle? So there's one at the top, or just where'd you start? Like that? So I got U, V all the way around? And then I can just draw the edges in, right? So UV, VW, VX, VY, WY, and XY. Yes? Okay. Did you lay this out in the same sort of circle?
Mine stretched, yeah.
Okay. Same sort of circle? I actually did not put this in a circle. U, V, W, X, Y. Okay, I just did them in alphabetical order, but straight down. Now, take a look at the edges. U to V, V to W, V to X, V to Y, W to Y, X to Y. Those are the same pictures. They are exactly the same. The way you choose to lay out the vertices can give you remarkably different pictures. And you don't know which one's going to look nicer or worse than the others until you try it a bunch of different ways. I 100% cheated. The picture on the right's the picture in the book. First time I drew it the same way you did. Okay. One of the larger problems in graph theory that we will touch on chapter 2 and 3 is in determining whether or not two graphs are really the same. An isomorphism problem. We're going to hear that phrase in a lot of different classes. The graph isomorphism problem is currently known to be NP hard. So we're not going to solve it. But we'll come up with some good ways to tell when graphs are different. Okay. Questions? Since we think of graphs as sets, I can say that I have subsets. If my vertices in one graph are completely a subset of the vertices in another graph, and the edges also are a subset, well, then I've created a subgraph. And we would actually use that subset notation and say H is a subgraph of G. We talked about back in chapter 2 in discrete proper subsets and improper subsets. A proper subset is different than an improper subset because of what?
Because it is less than, it
And-
doesn't have all the points and all of it.
And not equal to. So a subgraph can be called a proper subgraph if it's absolutely contained in and not equal to. Now, that could mean only removing an edge. It could mean only removing a vertex. It could mean a couple of different things. But our goal is to try and think of a proper. So therefore, the only improper subgraph is the whole thing. You just kept everything. Why are you giving it a new name? If I keep all the vertices, but I don't necessarily keep all the edges, we call that a spanning subgraph. I hate that term. Because to me, spanning means something else that we'll talk about later. So it is a technical definition in the book. I don't like that definition. But I'm going to stick with it because the textbook uses it. I will give you what I think is a better definition of spanning later. Questions? F is an induced subgraph of G. Okay, it's a subgraph. Subgraph means it has either fewer vertices or fewer edges, or both. The word induced means that if I keep the vertices, I keep the edges between them. So let's suppose we have two vertices that are in the subgraph. I must if there is an edge between them, keep that edge. Now, this again sounds stupid, but let's go back to the picture we just looked at. I want you to take some of the vertices. There are 5. How about you pick 3 of them? Which 3 do you want? We'll throw the other 2 out. Now, here's the deal. By saying I want the induced subgraph, I decide which edges will go here by asking which edges from the original graph still connect these things. Those are the only edges I'm allowed to use. So this will end up only having those 2 edges. When I took away the other vertices, I took all of the edges that touched them. And thus I've induced a subgraph by naming this collection of vertices and taking the pieces that got taken away, took their edges with. Talk to me.
If you had U, X, and Y, how would you write that? Just use something next to the P.
I'd end up with a graph that had 2 pieces in it. But you're absolutely right. The only edge I get to keep is the edge between X and Y. When I threw away V, I threw away the 4 edges that were incident to it. When I threw away W, I threw away the additional edge incident from W to Y. Now that's actually an interesting difference, because this new subgraph is definitely different than the other one. There's a fundamental characteristic that's different. So this is an important idea of what sort of things we want to think about. I would call this a vertex-induced subgraph. We picked the vertices, we then decided which edges we were going to keep as a result. If you have any subset of the vertices, then you can create a subgraph induced by that set, as long as it's not 0. Because the empty set doesn't have any vertices in it. You have to have vertices to have a graph.
Graph be a subset of one that is full. Or not full, but has vertices.
Our definition of a graph meant we had to have at least one vertex.
Okay, so then S couldn't exist if it was 0.
You cannot induce on no vertices. There's nothing here. I have to have at least a vertex. I don't have to have edges, but I have to have at least a vertex. A dot all alone. That's a graph. One vertex, no edges. Order 1, size 0. That's why those 2 characteristics are different from one another. I could go the other way. I could ask you to pick edges and then decide on the graph from that. So I have a vertex-induced subgraph. I can create an edge-induced subgraph. Here I could use, but I don't want to. So I'm going to say that our set cannot be empty again. So whenever you take an edge, you keep the vertices at both ends. You can't have an edge that only has one vertex on it. It's got to have a vertex at each end. It's got to have endpoints. They've got to be segments, like in geometry, you have A, B. You can't just keep going. You have to have ends on each side. Vertex-induced subgraphs are more common than edge-induced subgraphs, but we will run into them occasionally. Sometimes, instead of using these sorts of square bracket notations, you'll also see a notation that looks like this. That sort of angle bracket is a group theory term in terms of a generating set. If you haven't taken group theory or are going to take abstract algebra, you'll see it there. If you're not going to take it, darn. That's okay. Questions? We chose vertices and said we were taking away other vertices, right? We could think of taking away edges or taking away vertices, right? I could just take away edges and leave the vertices behind. I could take away one edge or multiple edges. I could take away one vertex or another vertex. Here's my set X, right? I could think of G take away X as having the same vertex set, but taking away the edges. If I want to take away a single edge, I could just write G minus that edge. But when I take away vertices, I take away the edges with them. So if I take away a vertex set, every time I take away a vertex, I have to take away every edge that's incident to it. By the way, adjacent means what again? Adjacent vertices? They're connected with an edge. So non-adjacent. Hello? Non-adjacent vertices means that edge isn't there. But I could make a bigger graph by adding that edge in, couldn't I? So the picture we had earlier, I could say what I'd like to do is add the edge, I don't know, UX. And that would give me a bigger graph. It would have a larger size, wouldn't have a larger order. Order is the number of vertices, size is the number of edges. By the way, now, in this case, G is a spanning subgraph of this bigger graph because it's got the same vertex set and it has fewer edges. So there, I added the edge UX to my previously existing graph G. Question.
But for someone.
This graph is not a subgraph of G. G is a subgraph of this. Because I made it bigger, G is now inside. There. Okay. I like thinking of graphs like maps. One of the oldest graph problems started on a map. One of the original games of graph started on a map. This, by the way, has 20 vertices and 30 edges. And if you include the outside, it makes 12 regions. One ring of 5, another ring of 5 inside the next. There was a game based on this map. And the question was, could you visit all 20 cities? 20 dots. Can you visit them all? What does that mean? Were there particular things about the way you visited, order, or doubling back? So let's talk about moving on graphs. If I have a graph and I have two vertices, U comma V in the vertex set of G, I am going to describe a walk from U to V. As a sequence of adjacent vertices. That starts at U and ends at W. The requirement here is that k is bigger than 0. I have to, I mean, I could go from here to nowhere, right? I'm at vertex U, I'm going to go from U to U. I don't move, right? It's a 0 length walk, but I go somewhere. And the I plus 1 are adjacent. 0 less than or equal to I, less than or equal to k minus 1. So I can think of myself as hopping around my graph. The vertices are lay on the walk. They are the steps along the walk. The edges, vi to vi plus 1, belong to the walk. The walk we have written down up here has k edges. The number of edges is the length of the walk. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, all the way up to k minus 1 to k. This is commonly referred to as fence posting. If you need to make 5 10-foot lengths of fence, you need 6 posts. 0 to 1, 1 to 2. Aha. So I have a 0, I have k, that's the length of k. A walk of length 0 is trivial. A closed walk. What's a closed walk?
Where you can keep any, edges.
No, that actually does not go with the word closed. If I return to my starting point. Here's the interesting part. I have not said a single word about repetition. I could bounce back and forth 7 times between here and the next vertex, back and forth, and it's still a perfectly good walk. Matter of fact, I got a lot of steps in just moving back and forth, right? This is my stupid PT exercise. As I work on my hip abductors. Yay. I do that for 2 straight minutes and it hurts like. If I don't close my walk, we're going to call it an open. That's an obvious definition. If I want to limit repetition, I need to think about the way in which I will limit repetition. A trail is a walk that doesn't repeat an edge. Here's a graph. A walk might look like this. X, Y, W, back to Y, up to V, down to W. But that's not a trail because where? I go from Y to W, I go right back from W to Y. So that's not a trail. On the other hand, here's another walk. From U to W to Y to X to W to V. 1, 2, 3, 4, 5. That's a trail. No edge is repeated. All trails are walks. Not all walks are trails. But I still repeated, didn't I? I went through W twice. I didn't repeat an edge. I repeated a vertex. 1, 2, 3, 4, 5, but I hit W twice. Okay, so let's build a new category. A UV path is a walk that doesn't repeat any vertices.
Are you think you'd be there because that's the certain of the stuff?
Right, and I'm going to denote different paths, trails, and walks by where they start and where they end. And most of the time, the AV walk, AV path, I just need to label it somehow. I could talk about arbitrary trails and walks, but I need to have starts and ends. Because later I'll talk about closed paths and closed trails and closed walks, in which case I'll just need to know where I start. Please note, it's a walk that doesn't repeat any vertices. Every trail is a walk, but not every walk is a trail. Every path is a walk. Is every path a trail? Emily, you're nodding your head. Tell me why. You're not sure. It seems like it should be.
They don't look about circle.
Yeah, I don't even know where I'm starting and ending, right? Because it could be any looking graph. Do I have the ability to repeat an edge in a path? You also seem to indicate something wrong.
Yeah. Helps,
If I go back across an edge, don't I have to go back to a vertex I've already gone to? I have to repeat a vertex to repeat an edge. So every path is a trail as well as a walk. So now I have a hierarchy. I have walks. Go anywhere, repeat anything you want. I have trails. I only cover each road once. And I have paths. I only cover each stop once. These are objects that live in my graph in plain sight, but they aren't the objects the graph is made of. The graph is made of vertices and edges. And I can then think of a collection of walks or a collection of paths or a collection of trails as things to use. I can, for lack of a better term, add walks. I go from U to V with some walk, and I go from V to W with some other walk, right? Well, then I've built a walk that goes from U to W. I'm stealing from the computer science people. Concatenate means to just do one after the other. This comes from the Unix, the Unix library cat to command in Unix. You just do one after the other. So if I want to say I've got, as we said earlier, UV and then VW. However, yeah, I could take a section in the middle of a walk and say, here's another walk, but it's not going to connect the same pieces, right? If I take any piece of a walk, that's another walk. Here's a problem. If I add two trails, the result might not be a trail because I might have an edge that is in one that is now in the other, and suddenly I've repeated an edge. If I add two paths, I might not stay a path. I could have a vertex in one, show up in the other. Oh, crap. So walks is a category where it adds, but paths, when I add, I might not stay a path. Trails, when I add, might not stay a path. Trails. However, I like paths. I like paths the most because they have the least repetition. They're the simplest kind of object. If I can walk there, then I can get a path. Now, I've actually just written something on this piece of paper in front of you that should piss you off. I've written word family. I write the word theorem, what has to follow it? Yeah, I should prove this. The proof is actually fairly short. It's not truly a proof by contradiction, but it's close. Let's suppose I have a walk from U to V. I want you to now take the smallest possible walk. Because if I can get from U to V, then I can cut out extra steps. I'm not going to write out the formal proof here. I'm going to hand wave at this a little bit. Suppose the walk was a trail. I might repeat a vertex then, yes? Well, if I repeat a vertex, then I've got basically a loop that comes back to that vertex. Chop the loop off. You've made a smaller walk, haven't you? Because you made a trail, and a trail is smaller. But a trail that repeats an edge, if I remove the repetition, what have I made now? I've made a path because it no longer repeats a vertex. Every time in my walk, if I repeat an edge, just stop doing that. If I have to repeat it an odd number of times, just do it once. So I can write out from a walk, I can get to a trail really easily. From a trail, I can chop off any loop. Give me, well, not a loop, but a circle. I can chop off any circling back to force myself to have a path. There is a formal proof via contradiction in the text, page 13, I believe. It's worth looking at so that you understand the way this sort of proof would read. I have more ideas about paths and walking and traveling on graphs. I have run up against the clock, so we will do more of this on Friday. I will see you then. Have a wonderful rest of your day. Yay.